Hello and welcome to Nurture Academy. Today, on the request of many kids, we are going to discuss easy way of understanding the unit AC current. So to start with this chapter, we have to know number one, the difference between DC current and AC current. So the difference is that DC means direct current. It doesn't have any changing phase. AC means alternating current. It goes like a wave. Actually, not exactly like a wave, but we can say it is a alternating current which changes its direction every half cycle that it moves. So now, we are bothered in this chapter about AC current. So we will send AC current through different devices. For example, first one we are going to learn is AC through resistor. So we will take one simple resistance and through this we will pass AC current. Now all we need to remember is that the simple formula for EMF is given as E is equal to E naught sine omega t, where E naught is the initial value of EMF, E is the peak value of EMF, omega is the angular frequency. And please remember one more thing for reference, that omega is always equal to 2 pi divided by time period, or it is also equal to 2 pi nu. This will be very useful going further in this chapter. So further, when we pass AC through resistor, that time the formula of EMF is given as E naught into sine omega t. And if we say in terms of current, I will say current I is equal to E naught divided by R sine omega t. E is actually nothing but peak value of voltage. So here nothing but we are using a kind of Ohm's law. In Ohm's law, we were using the symbol V equal to I into R. But in this case, we will use the symbol EMF, E instead of V, but the sense is almost same only. And we can write it I is equal to I naught sine omega t. Here, if you compare the equation of EMF and the equation of current, we will say that resistance offered by a resistor to the flow of AC current is given by symbol R, and there is no phase difference between current and EMF when AC passes through a resistor. Next device we are going to pass AC current is called a inducer. Inducer is nothing but a kind of a solenoid. So we will draw one coil through which we will pass AC current. This symbol is for AC current. Base formula of EMF will write the same. E is equal to E naught sine omega t. You can also write small e if you don't want to get confused between symbol of electric field and EMF. Now, again we have to find the value of current. But in case when we pass a AC current through a inducer, we know that according to Faraday's second law, EMF is equal to minus L di divided by dt, where L is called the coefficient of self-inductance for a coil. And you should know that a coil will get self-induced. So instead of writing, directly I is equal to E by R, I am supposed to now equate equation number 1 with equation number 2, and then only I'll be able to find the value of current. So let's do that. We will get E naught sine omega t is equal to minus L di divided by dt. So what we are going to do in this case is that we will take this dt on this side. We will get E naught sine omega t into dt is equal to minus L into di. I don't want di, I want the value of I. Bring this L in the denominator, again cross multiplication. So we get E naught sine omega t into dt divided by L minus is equal to di. Integrate and integrate. After integrating this equation, we will get the value for current. So we will get I is equal to E naught divided by omega into L multiply by sine omega t minus pi by 2. Why I got this expression? Because I know that after I integrate sine, I will get the answer in terms of cos. To compare it with my base equation, E is equal to E naught sine omega t, E is equal to E naught sine omega t. Just to compare this, now I will understand two things. First is the resistance offered by inductor to the flow of AC current is given as 1 upon omega L. You can see here, sorry, not 1 upon omega L, it is omega L, right? And this resistance is not called resistance. It is written by symbol XL. The resistance offered by inductor for the flow of AC current is written by the symbol XL. It is called inducive reactance and it is equal to omega times L. Plus, if you notice the lag between omega t and omega t minus pi by 2, so we can say that the voltage lags the current, voltage leads the current by an angle of pi by 2. Voltage leads current by pi by 2. This is when we send the AC current through a given inducer. Now, third and the last thing, we have to send the AC current through a capacitor. This is also very simple. So we will just take one capacitor and we will pass AC current through the capacitor. This time, same as always. First, we will write the base formula. E is equal to E naught sine omega t. Now in capacitor, if you remember, EMF or voltage is equal to Q by C, where C is the capacity. Now I don't want charge, I want the value of current. So I know that very clearly, current is equal to rate of change of charge, right? So now, I will fill the value of Q from equation number 1 into here. I will get I is equal to d by dt of E times C. Now I will fill the value of E from this equation into here. So I get I equal to d by dt of E naught sine omega t multiplied by C. And all I need to do is solve this differential equation. So after solving this differential equation, I'll get the answer. I is equal to E naught into multiply by omega C into sine omega t plus pi by 2. Again, after differentiating, I get the answer in terms of cos. But I want to compare it with the equation of EMF. So I'll convert the cos into terms of sine. Another thing is that I want to find now the value of resistance. Resistance is given as current is equal to EMF divided by resistance, right? Here individual factor, nothing is there. So little smartly, I'll use the math and instead of writing this one, I'll convert it into E naught upon 1 upon omega C. So in this case, I can say the resistance offered by a capacitor for the flow of AC current can be written as 1 upon omega C. Again, it is not called resistance. It is written by symbol Xc, which is called capacitive reactance. Okay, so now we have passed the AC current through three devices, one resistor, one capacitor, and one inductor. Also, we have noticed that in this case, current leads the voltage by a phase angle of pi by 2. So in case of inducer, the current lags. In case of capacitor, the current leads. Now, in the given numerical, these guys will give you a LCR circuit. The circuit which will contain resistor, inducer, and capacitor. All three together. And then we have to figure out what is the total resistance of the circuit. Here we can smartly use little vector diagram to come to the conclusion. How? For resistance offered by resistor and current, both are in same phase. So I'll write it here. Resistance offered by a inducer, I can write here as XL. Resistance offered by a capacitor, since it is behind, so I'll write like XC. First thing, I will find the net result for XL and XC, which will be automatically in this direction, which I am drawing with red color arrow, and it will be written as XL minus XC. Second task, I need to find the resultant between XL, XC and R. Supposing the angle between them is theta, and you guys know that the value of theta is 90 degree. When I apply vector sum formula, I can say that net resistance is given as under root of the formula of resultant of two vectors is a square plus b square plus 2ab cos theta. Here cos theta value is cos 90 degree, so it is 0. That's why I can directly say it is equal to XL minus XC whole square plus R square. Now what is this Z? Z is called the total resistance of LCR circuit, which also have a fancy name. It is called impedance of the circuit. Okay, so I hope until now you have clearly understood how to pass AC current through three devices and how to calculate the net value of resistance, which is called impedance. Now, supposingly I want the minimum resistance in the circuit, but I want to keep all the three devices, capacitor, inductor, as well as resistor in the circuit. So what should I do? If you browse through this expression very clearly, you will know by chance if XL is equal to XC, that time comfortably we can get minimum resistance. So this type of circuit where XL is equal to XC is called resonating circuit. And now we fill the value. XL is equal to omega L, XC equal to 1 upon omega into C. So when you keep omega on same side and you solve it, you will get the value as 1 upon root of LC. Suppose they are asking calculate the frequency of this AC current. So you know omega is equal to 2 pi nu. Already I told you to remember it. Fill that and you get nu is equal to 1 upon 2 pi root of 1 upon LC. So this is the value for frequency of a resonating circuit. And here we can also define something called quality factor. It's not necessary that in an AC circuit, we will get current only at one position, because we are always writing I equal to I naught sine omega t plus or minus pi by 2, right? So we can also define something called Q factor or quality factor. Quality factor is actually seen in radio waves also. When you tune your FM radio, that time you notice if some channel is supposed to play at 108 frequency, before that you'll start to hear some kind of sound like rrr, and after that also. Same is in the case of AC current, since it is a kind of having a frequency. So if I plot the graph between current and frequency, and I get a kind of a band, that means this signal is poor in quality. But if I get a very, very sharp signal, that means it is a good quality signal. But how do I calculate the formula of quality factor? So quality factor calculating is very, very simple. It is written as voltage across L or C divided by applied voltage. Okay, and here we can also say that Q factor can be written as 1 by R root of L by C. Okay, this is the value of quality factor. Now, the most important thing in this chapter to learn is what is the power in the AC circuit. So to calculate power, always remember the generic rule of current electricity. Power, very important. Power is equal to EMF or voltage multiplied by current. Now fill the value, you will get P is equal to E into I. E is equal to E naught sine omega t. Instead of I am supposed to write I naught sine omega t plus or minus pi by 2. Why I'm writing plus or minus pi by 2? Because it can be plus or it can be minus, right? So plus or minus pi by 2. And after solving this thing and taking its integral over time, I will get the value of average power in a AC to be equal to E naught I naught divided by 2 multiplied by cos phi, where I can split it further, E naught by root 2, I naught by root 2 into cos of phi. That is P average. Now E naught is called root mean square value of voltage. I naught by root 2 is called root mean square value for current, and cos phi is called the power factor. By the way, this angle phi is the angle which in a LCR circuit, the total resultant impedance which subtends with one of the factors. That is the angle phi. And that was all about AC currents. So if you like our videos, please like and subscribe to our channel and also share our videos. Thank you so much.